Hi, I'm Yuanbo Xiangli, and I'm here to talk through our work, Honey, I Shrunk the Triomphe. This work is jointly done with Hanyu, Xueqing, and Noah. State-of-the-art monocular geometry estimation methods like MOG2 exhibit a persistent scale collapse phenomenon, where far-field structures are metrically shrunk and put towards the camera. We deduce that this performance gap is due to limitations in available training data. Current metric scale real-world datasets are restricted to two narrow categories due to hardware constraints, including terrestrial LiDAR datasets like Kitty and Argoverse, and active 3D scanner capture data like ScanNet and ArcScene. Synthetic datasets, on the other hand, fail to capture the true metric diversity of the real world. In this work, we introduce metric scenes, a large-scale dataset curated from a variety of commonplace visual sources, including internet photo collections and stereo videos. We gather imagery from aerial megadepth and megascenes, which consist of diverse internet-sourced photography. Specifically, aerial megadepth is reconstructed with pseudo-synthetic veils rendered from Google Earth, and the scenes are scaled accordingly. Megascenes contains natively unscaled structural motion results, so we augment these models with georeferenced street-level views to scale the geometry to physical dimensions. After scaling and running MVS, we apply a depth filtering step to remove transient objects and filter out depth-leading regions. The Stereo 4D dataset provides a collection of diverse, real-world stereoscopic video sequences captured using VR180 devices. For each video clip, we sample a target center frame and extract its surrounding frames, forming a chunk. Then we pass this chunk to a multi-view reconstruction model like PyCube to jointly estimate camera poses and scene geometry. This approach leverages broader spatial-temporal context, leading to more accurate and consistent depth estimates than using a single pair. We recover the absolute metric scale for each scene by aligning the average predicted baseline between the reconstructed stereo pairs to the non-physical baseline extracted from video descriptions. To further ensure data quality, we discard underposed and motion-blurred frames, perform a depth reprojection check on the stereo pairs, and reject frames that violate expected stereo constraints. However, depth maps from prior stages are typically incomplete. Internet photos lack foregrounds and transient objects, while stereo imagery lack background due to low confidence in distant points. Directly fine-tuning on such partial depth maps results in incomplete structures and erroneous foreground depth. To reconstruct the missing regions, existing methods use a logarithmic space Poisson completion algorithm. Specifically, it integrates the incomplete ground truth depth map with guidance from a monocular depth model like MOG2. However, we noticed that because of the scale collapse issue, when the depth difference between the foreground and background is large, this approach yields incorrectly enlarged foreground. A naive solution is to use both the MVS background and MOG2's foreground as fixed anchors, but then unanchored transition regions will be warped toward the foreground to satisfy global gradient constraints. To fix this, we propose a two-stage edge-aware completion pipeline. In stage 1, we use only the sparse background depth as anchors. This will result in complete depth maps where the background is at a consistent metric scale, although the foreground is enlarged. In stage 2, we combine the completed background from stage 1 with MOG2 predicted foreground to form a composite anchor. To further preserve sharp boundaries, we utilize an edge-weighted objective where the weight Wij approaches zero across sharp depth discontinuities. With this strategy, we effectively address scale confliction and boundary distortion. We fine-tune MOG2 on our metric scenes dataset and name it Wild MOG. Results show that Wild MOG consistently recovers more accurate absolute scales across diverse scenes, whereas previous methods all underestimate the scale of background structures. On the standard scenes, Wild MOG provides scale estimations consistent with or sometimes better than MOG2. We further show that fine-tuning on our dataset can also significantly improve other depth models' performance on in-the-wild scenes and yield gains on standard benchmarks in some cases. Please visit our project page for more details. Thank you.